We have to find the RMS value of alternating current, that is RMS value of AC. The instantaneous value of alternating current is I, which is I0 sine omega t. And I0 is the peak value of alternating current and omega t is the angular phase. We consider a circuit containing a resistor of resistance R and which is connected to an AC source. This is an AC source. This is an AC source of EMF E equal E0 sine omega t. E equal E0 sine omega t. This is an AC source which is connected to a resistor of resistance R. And here instantaneous current I equal I0 sine omega t is generated from the AC source and which is also flowing through the external resistance capital R. When the alternating current I equal I0 sine omega t is flowing through the external resistance R, the external resistance R generates heat energy H. Now, what should be the definition of RMS value of current? The RMS value of alternating current, is defined as the constant current, under bracket I.R.m.s, which is defined as the constant current, and we can consider a circuit diagram in which a resistance capital R is connected to a constant current supply, and this constant current supply produces a constant current I.R.m.s. If this constant current I.R.m.s flows through the external resistance R, a heat energy H prime will be produced. In this case, R.m.s is the constant current and I equal I0 sine omega t is the variable current. And this resistance capital R produces a heat energy H prime when constant current I.R.m.s flows through the resistance. RMS value of alternating current is defined as the constant current which produces the same heat energy in a resistor under bracket capital R, which produces the same heat energy in a resistor in a full cycle as is produced by the alternating current under bracket I equal I0 sine omega t in the same resistor in the same cycle, or in the same time interval, or in the same interval of time. Now we can consider that H is the total amount of heat energy produced by the resistance R in both positive half cycle and also in negative half cycle. Now the heat energy produced in the resistor, of resistance R connected to the AC source by the alternating current under bracket I equal I0 sine omega t in the same interval of time. Heat energy produced in the resistor of resistance are connected by the AC source by alternating current I equal I0 sine omega t in the small interval of time dt is given by dH, which is I square R dt. Therefore, dH is equal to I naught square sine square omega t R dt. Therefore, the total heat energy produced total heat energy produced in the resistor of resistance R is given by the alternating current. The total heat energy produced in the resistor by the alternating current I equal I0 sine omega t in full cycle. In full cycle is given by H equal integration dH 0 to t. Integration 0 to t dH is equal to integration 0 to t I naught square sine square omega t r dt. Now I0 and R are constant. We can bring I0 and R outside and outside the integration. Therefore, I naught square R integration 0 to t sine square omega t dt. I naught square R divided by 2 integration 0 to t 2 sine square omega t dt. H is equal to I naught square R divided by 2 integration 0 to t 2 sine square omega t dt equal I naught square R divided by 2 integration 1 minus cos 2 omega t dt. I naught square R divided by 2 third bracket, and first we should consider the third bracket, then integration dt 0 to t third bracket integration dt 0 to t minus integration cos 2 omega t dt 0 to t equal I naught square R divided by 2. So integration dt becomes t, integration dt becomes t under third bracket t 0 to capital T minus under third bracket sine 2 omega t divided by 2 omega 0 to t equal I naught square R divided by 2 t minus 0 1 by 2 omega bracket open sine 2 omega capital T minus sine 0 bracket closed. I naught square R divided by 2 t minus 1 by 2 omega. Now putting the expression of angular speed omega, we get sine 2 in place of omega we can write 2 pi by t into t minus 0 bracket close. I naught square R divided by 2 equal t minus 1 by 2 omega under bracket sine 4 pi minus 0, and we get I naught square R divided by 2 into t minus 1 by 2 omega. Sine 4 pi is 0. So finally we get total heat energy produced in the resistor R as half I naught square R capital T, where capital T is the time period of oscillation of alternating current. H is equal to half I naught square R T, half I naught square R T, which is equation 1. Now a source of constant current is connected to the external resistance capital R, and constant current, that is R.m.s, is generated from the source of constant current, and this constant current produces a heat energy H prime in the external resistance capital R. Again the amount of heat energy, produced, the amount of heat energy produced in the same resistor capital R, by the constant current, that is by the RMS value of current or RMS current under bracket IRMS in full cycle or in the same interval of time, is given by H prime equal IRMS square R into capital T, where capital T is the time period of oscillation of alternating current. H prime is equal to IRMS square R T. Now H prime is equal to H, that means heat produced by the constant current IRMS is equal to heat produced by the alternating current. Therefore IRMS square RT equal half I naught square RT, or comma IRMS square equal I naught square by 2. Therefore IRMS is equal to I naught divided by root 2. IRMS is equal to I naught divided by root 2. That is the RMS value of alternating current. Here IRMS is equal to I naught divided by root 2. So this is the RMS value of alternating current. IRMS is equal to I naught divided by root 2, which is the RMS value of alternating current under bracket I equal I0 sin omega t. Therefore, I.R.m.s equals 0.70 times of I naught. I.R.m.s is equal to 0.70 I naught. That is, RMS value of current is 0.707 times of peak value of current. Again, I average equal to I0 by pi, and I average can be written as 0.637 times of I naught. And I.R.m.s is equal to I naught by root 2. That means I.R.m.s is equal to 0.707 times of I naught. Therefore, I.R.m.s is greater than I average. RMS value of current is greater than the average value of alternating current. I.R.m.s is greater than I average. Now we can represent the positive half cycle of alternating current. Sinusoidal variation of alternating current. This is the sinusoidal variation of alternating current in positive half cycle. Along y-axis or in along vertical axis, current is plotted. Along horizontal axis, time is plotted. We can denote peak value of current at time t equal t by 2. At half cycle, we get the peak value of current I0. Peak value of current I0, and if we consider half of peak value of current, that is 0.5 of I0, and this current is peak value of current I0, that is the maximum value of alternating current. Now we can denote average value of current. This is 0.637 times of I naught. This current is equal to 0.637 times of I naught, and that is the average value of current IAV. This is the average value of current. This is the average value of current IAV, which is 0.637 times of I naught. Now we can denote RMS value of current. This is the RMS value of current, which is greater than the average value of current. And this current is 0.707 times of I naught, and that is RMS value of current, or I.R.m.s. This current is I.R.m.s, which is denoted in positive half cycle. Therefore, I.R.m.s divided by IAV equals 0.707 times of I naught divided by 0.637 times of I naught. Therefore, I.R.m.s divided by IAV equal 1.11. I.R.m.s divided by IAV is equal to 1.11, and that is known as the form factor of alternating current. I.R.m.s divided by IAV is equal to 1.11, which is defined as the form factor, of the alternating current, and that has a value 1.11.